Hello students. Okay, today we are going to discuss about time independent perturbation theory. So we have discussed about perturbation theory in the last video briefly, and I have given you an overview what is actually meant by perturbation theory. And we have seen that there are perturbation theory that is applicable for time dependent systems, time independent systems, and right now we are going to deal with the time independent perturbation theory, the most simplest case. So here also we have two classes by which the time independent perturbation theory is going to work. One is for the system which are non-degenerate, so this is going to be the simplest among all, and another one is for degenerate system. So what is the difference in the case of when the degeneracy is coming? The difference is that there is a chance that these states which are degenerate, when you apply the Schrodinger equation after it not necessary that it has to be in the same degeneracy state after your perturbation happen or the change in the Hamiltonian happen, whatever sort of change it is. After the small change happen, it's not necessary that all of them are again degenerate, not always. So there is a kind of confusion regarding that. So this is a simple case where we have all states are separate, so there is no degeneracy sort of thing. So to briefly mention why we are using perturbation theory is to find out solution for the problem for which we don't have an exact solution. That means we want to solve the Schrodinger equation for a particular problem for which we don't know exactly how to solve it, but we may be having some solution for a kind of system which is somewhat close to the Hamiltonian of the system for which we need to find out the solution. So the example that I have given you is a square well kind of a system. You know that square well potential, how okay, let us take a square well potential, and it's an infinite square well potential. So boundaries with the potential infinite, and inside that we have potential 0. So you know the exact solution of this particular system, and you know the energy eigenvalue En. What is that? We have a clear equation for that, and we know what is the wave function for that. Different possible wave functions like root 2 by L sine kx by L, whatever, kx by x by L or whatever. So that equation you know. So let us say right now I have a case where I don't have the problem exactly like that, but I have the potential, that is a slight variation, that is this sort of a potential I need to solve. Right now it's kind of similar like our infinite potential well, but at the bottom of it there is a small distortion. So how do I find out the energy states of that system? Is it going to be the same as the previous case? Obviously it is not. There is going to be some sort of change. And what sort of change this is going to have? What about the wave function? What about the probability? If the wave function changes, the probability will changes. So everything will be slightly modified. So this is a real thing. So even though you want to solve this problem, at some cases you can take the solution is somewhat like close to the square well potential problem itself, if you want no correction of any other sort. But if you want a little more precise measurement, just like in the case of numerical methods what we are doing, we have to do an order by order correction depending upon the accuracy that you want, right? So okay, so in this case let's say for our infinite potential well, these are the energy states of our infinite potential well. So En, this is correspond to E0, E1, etc. up to En. These are the different energy levels for the infinite square well potential, the before the perturbation is introduced, that is our known problem kind of. Now after there is a slight perturbation for the system, what will happen? Of course the energy may change. So how much it will change? It will not be changing drastically to very high value. If the perturbation is very small, so it can change up to, let's say En is changed to this level, n minus 1 is changing to this level, and even E ground state is changing that much. So every state will be having some sort of a correction. So what we want to take is to incorporate this correction and find out the exact energy level after this perturbation is being introduced. So that means we are solving the problem of not the actual square well potential, this one. So that is how we proceed. Now okay, let us take this as a reference case to solve or to understand the problem. So let me take the Hamiltonian of this system, the system which is modified, that is the unknown system. The Hamiltonian of the system, I'll take it as H cap. So it's unknown Hamiltonian. Alright, I'll use black ink. Okay. So corresponding to that problem, we will be having a state that is psi. I take the state of the problem that we are defining right now as psi n, and this is the state of our unknown system. This is the state of our unknown system. Okay, now what is the Schrodinger equation here? It's a time independent wave function because we are dealing with time independent form of an equation. So H cap acting on psi n, H cap acting on psi n will give you its an value, right? So this is the Schrodinger equation of our unknown problem. I'll call this as equation number 1. That is something that we have to solve. So after solving that, what we will be getting? We'll be getting one we have to get is the energy and values En. Another thing is that we have to find out what is psi n. So we have to find the state and energy both of the system. So this is our aim. Okay, for which what we are doing is so this is actually the Hamiltonian of the perturbed system. So what I am going to do is, I know the solution of this square well problem, so I will take that as my H naught. So I will take an H naught. So H naught is my non-Hamiltonian. And corresponding to that, I know the state and I call that phi n is the it's a known thing. This is something that we have clear idea what it is. Okay, let me clarify that right now itself I am going to take this as an orthonormalized system. I mean the known solution I am mapping on a Hilbert space by using different vectors. These are n vectors, right? Phi n consists of different n vectors, and yeah, this is actually not the state. It's yeah, they are the n vectors, phi 1, phi 2, phi 3, etc., and one of that corresponds to a particular state. So these are orthonormalized things. So phi I, phi j is equal to delta ij, because that is how I define it. It's a non thing. I don't have any I'm not we know this thing actually. And also it will obey the completeness condition, completeness. So that is m phi m phi m is equal to 1, right? Yeah, so that is a completeness condition. So what will be our Hamiltonian equation for the non-problem? That is nothing but h naught acting on psi phi n is equal to En naught phi n. So this is the Hamiltonian equation that we know exactly. So this I will give number 2. This is a non-problem for us, and you know there is a superscript here, a subscript here. The subscript corresponds to the state of the system n, and which state you are referring, 1, 2, 3, etc. So subscript refers to the state of the system, whereas the superscript corresponds to the correction, which order of correction this is. So let me call this as a 0th order correction. So the least I can get the solution, that means my approximation is that my first approximation, it's not first order approximation, something if I have a system like this sort of a potential, I don't want to go to the first order correction anything, I just want to get an immediate solution. So within that accuracy you will tell, okay, then the solution of the problem is En0, it's going to be closely this value, you will say that way. So it's kind of a 0 order correction, that's why I put the number 0 here. Now depending upon the accuracy you want to put additional numbers over there, first order correction, second order correction, etc. So that will be mentioned on the superscript. So this idea you have to keep in mind. Whenever you are having a superscript, you are referring that as a correction term. So h naught here refers to the correction. So yeah, that is the reason I have kept the 0 in the superscript. You can see in several books it is actually coming in subscript. That is okay, because there is no subscript for the Hamiltonian, as it is an operator. There is no state contribution coming, it's an operator. So you can put it in the subscript also, there is no problem. To make it uniform, I'm putting it on top. Okay, so this is the idea. Now let us our idea is not to solve the non-problem. Our idea is to solve this equation. For the this equation, in the sense h psi n is equal to En psi. So this is the equation that I am interested in. So what I can do is I can split my Hamiltonian into 2 parts, and my first part of Hamiltonian is h naught, and I am telling that the Hamiltonian is having a correction term. So first term is the non-problem Hamiltonian, that is h naught, and I am adding remaining whatever comes as my perturbation to that. So I have a second term, that's a perturbed Hamiltonian. So whatever coming extra is a perturbed Hamiltonian. So this kind of a splitting I am doing for my Hamiltonian. So my unknown problem now become a non-Hamiltonian plus a correction term. Okay, so now when we can apply this kind of a case is only when this h cap p, that is you are adding the correction, and that correction should be smaller than the actual Hamiltonian, it has to be smaller than the Hamiltonian that we know. So there should be difference. It should be a smaller quantity. So what is actually mean by a small Hamiltonian? Small operator. An operator is smaller. How do you know that an operator is small? Or how do you make sure that the operator is small? Well, it's not very obvious. It's not clearly obvious because operator is a matrix and a lot of elements are distributed, and how do you check the operator is smaller? Of course, the number of the values of the matrix element will be small for a smaller Hamiltonian compared to the elements over here. That's true. So to state that fact explicitly, what you can do is to introduce a scalar number over here, and we can say that that number is going to be extremely small, so that this perturbation, that operator, is also going to be small. So in that way we will use like h is equal to h naught plus some constant, say unit free number, is multiplied with this Hamiltonian, and I just modified the term. Now I have written hp over there, so I'm writing h1. So the correction term in Hamiltonian, I just call that as lambda h cap 1 h1, yeah, lambda h1. So this number lambda is having value ranging from 0 to 1. So let's say this number that means you are multiplying it with the second term, you are multiplying it with the kind of a fractional number, and that term is going to be smaller. So if you want to assure that the term is going to be kind of smaller, you can choose the lambda value depending upon that, as lambda is going to 0.1, 0.01, 0.001, etc. Even though the Hamiltonian, the correction of this term is bigger, you can make it lambda smaller such that this entire term is going to be smaller, like that. So that is the idea of introducing this kind of a scalar number. Okay, so now our Hamiltonian is modified into this fashion. So we will be using this equation so frequently, so we'll write it another number 3. So h is equal to h naught plus lambda h dash. Okay, now we splitted our Hamiltonian. Okay, one thing we have to make sure while doing, or we are just bothering only about the cases where these Hamiltonian are Hermitian, or h dash, h1, h naught we know it's, so all are Hermitian. To make sure that the ion value that is coming out is going to be real, it means ion value which is coming out is going to be real. So that is something that we know about that. Okay, so we have 3 equations now. Now what we have to do? Now we have to solve this particular equation. So this is a most important part of this perturbation analysis, that I can write my wave function psi. This is an unknown wave function psi. I can write that as a power series starting from unperturbed state. Unperturbed state means it's nothing but, in this case we have given a number phi n, right? Phi n, it's starting from phi n. So So this is nothing but psi n 0, psi n with the 0 correction. 0 order correction is nothing but phi n. So I will write it as phi n plus another term, the second term which is coming. Sometimes I will be using psi n 0 extra, kind of when you're putting that number, that will become psi n 0, but psi n 0 and phi n both are same, that you have to understand. Okay, so that term lambda, another one is lambda. Okay, now we don't have phi, what we have is psi n 1 first order correction plus lambda square into psi n 2, etc. So we will not be going beyond this lambda square, we will always stop it here. So second order correction, that is maximum that will be going by using this methodology. Psi n is this quantity. Similarly, we can expand our En, energy ion values, as En 0 plus lambda En 1 plus lambda square En 2, etc. So this is actually the most important part in our perturbation analysis, that we can expand the state and ion values in the power series of lambda. So okay, this is also something that we will be frequently using. So I'll just put, I'll not be referring it, but just 4, 5. Okay, so what else? If you know these things, we can substitute the same values into our unknown problem. So our Hamiltonian is changed now. Our Hamiltonian is nothing but h naught plus lambda h1, that is my Hamiltonian of unknown problem, into psi n. Now psi n is nothing but phi n plus lambda into psi n 1 plus lambda square into psi n 2. So yeah, all right. Now which is equal to En 0 plus lambda En 1 plus, okay, lambda square En 2. These are nothing but scalar numbers, nothing to worry about that. And the state coming, that is exactly the same thing, phi n plus lambda phi n 1 plus lambda square sorry, phi la psi n 2. Okay, I think it is readable. Okay, so now what we have to do is to find out the similar terms. Okay, what will happen now here? This h naught is going to act on phi n. That is not having any lambda term, so that's kind of a constant. What we have to do is we have to equate the powers of lambda. See, on an equation, on a polynomial, this kind of a thing we have seen. we have on LHS the squares of a power, let's say x, that is not going to be equal to the RHS squares of x square or x cube kind of thing. It will be equal to that x term. Similarly, here we have lambda. hmm? This lambda is having a power 1 in LHS. That means that will be having, it is equal to the term in the RHS which is having a similar power of lambda. So what we have to do is we have to compare the coefficients of different lambda value. So what and all are the possible lambda values that it can come here? We will go up to lambda square. So first possibility is that the term which is not involving any lambda, that is h naught into this phi n, that is not having any lambda value. So any other term here involves that kind of a term? No. In LHS we only have one term, h naught and phi n. So we are comparing the powers of lambda power 0, and what we are getting is h naught into phi n is equal to en naught into phi n. So that is when we are comparing, there is no other term. En naught is there here, and phi n is there here. Apart from that, there is nothing. All other terms are having lambda. Now we'll compare the square lambda power 1. Lambda power 1, what and all terms are coming here? Let's say h naught. We'll start with h naught. H naught multiplied with this term will be having a lambda. Also h1 multiplied with this term also will be having a lambda. So these are the two terms in the LHS which is having powers of lambda. So that will give you something like h naught into psi n1 plus h1 into psi n, which is nothing but phi n 0. Phi n, no need of 0. Phi n, which is equal to, in RHS we will be having en0 multiplied with the psi n1 plus en1 multiplied with the phi n0. So this is another equation. So give the number for each equation. So the first equation is actually something that we already given number. So far we have 5 equations. Okay, let me call these 3 together as sixth equation, then we can refer them together. No, I will give it separately. So this is my 6th equation, this is my 7th equation, and lambda power 2. Comparing lambda power 2, it's actually we need not to see there, we can write it immediately. So to produce lambda power 1 with h naught, we need it to be multiplied with the psi n 2. Okay, to produce the h1 with the psi n1, if you multiply again it will produce lambda. And another possibility is that to multiply h2 with the psi n 0, but h2 is not there, we have only one correction term of our Hamiltonian. So that is it, actually that's it, there is no plus term. h1 h2 is not there, so yeah. Okay, now in the RHS we will be having three terms, right? En0 multiplied with the psi n2 plus En1 multiplied with the psi n1 plus En uh, 2 multiplied with the phi n, we will call, okay, phi n. So these are the three terms, and I call this as equation number 8. Okay, so now what we have to do? Okay, so first thing that we have to do is to find the correction. So already we have zero order correction, that is nothing but this equation, you know, this is nothing but our, so this is the zero order correction, and it's nothing but our non problem. That is a zero order correction, right? If you want to solve the problem, okay, I don't want to bother. It's kind of close, which value is kind of close to the kind of our unknown problem, that will come as our solution for our first guess. Now I want a little more precise. I want to go to the lambda 1. So corresponding energy, ion values, and the state, both of them I need to find out. So this is actually, you cannot find out the state before you find out the energy. So first you have to find out is to find out the En1, first order correction in energy. Okay, let us do this first order correction in correction. Both energy and state will be coming there. So to do the first order correction, let's see these equations. So where is this first order energy term coming in? So this is the Hamiltonian part, energy part. First order correction is coming here, right? Energy En1. En1 is multiplied with phi n. Okay, there is no need of this zero. That's phi n, right? Otherwise you have to write it psi n 0. This is phi n. So you are multiplying En1 with psi n here, and that is a term which is having any first order correction of energy. So this is a quantity that you want to find out. So how do we find out that? Well, one way to do is to multiply the entire equation with what bra of this quantity. So what will happen is that bra will be multiplied here. So this is actually a number En1. So that bra and this get together will be kind of producing a scalar product. And if it is same state, it's an n state, if you multiply it with the n state, that will give you, you know, that is this phi n is coming because of the normalization, orthonormalization. Phi n will come, which will come as 1 for you. So you will get this term. If you are multiplying with some other phi n, that is going to be 0. So that is not useful for us. So we have to do it multiplication with this phi n itself. So bra of phi n, we will multiply the entire equation. So what we are going to do is to multiply the 7th equation with the multiplied with the phi n. This is something that we are going to do. Okay, now we have to see what is there in the LHS. LHS we have H0. If you do that, what you are having is phi n H0 and psi n1 is your first term, and you have phi n h1 and phi n, which is equal to en0 into phi n1, right? en0 into phi n into psi n1, okay, plus en1 into that term that I already told, it's kind of 1. Okay, so now how do we solve this part? Here we have an h0 operator. H0 operator is something that we know, and when it is acting on this phi n, it's kind of going to produce you the eigenvalue equation, but only the thing is that it's acting on a bra. So what change the term eigenvalue will be having? The eigenvalue, yeah, if it is just, if it is not a Hermitian system, if it is not a Hermitian operator, that will be producing a complex conjugate of that energy value, but this is a Hermitian operator, so it will produce exactly the same eigenvalue here. It will produce En, it will produce En there, En0, right? Yeah, En0, and you have phi n and psi n1, phi n psi n1, plus this quantity, that is phi n h dash phi n, is equal to En0 phi n psi n1 is there both side, okay, there is no need to solve it. En0, let me write it here, phi n psi n1 plus what is remaining is nothing but En1. So this quantity is there on both sides of the equation, and that will cancel. That two terms will be going. So you got En1, the first order correction in energy. En1 is nothing but phi n h dash phi n. So this is kind of our correction, first order correction in energy. It's a correction, it's not the energy, entire energy, it's a correction term. Okay, what is the number of the equation? We put till 8, so this is 9. Okay, you got En1. So what is the energy of that particular state E with the first order correction? Okay, En is nothing but En naught plus, with first order we know that series lambda En1. So En naught is nothing but En naught. En naught plus lambda multiplied with this particular term, right? Lambda into phi n h dash phi n. Okay, so now lambda into this h dash, it's a scalar number, you can easily go through this. So lambda into h dash is something that we call the perturbed Hamiltonian HP. So you can write it in terms of HP. It's not necessary, it's already, you can write in terms of h dash also. There is no harm in doing that, but yeah, En En0 plus phi n HP phi n is your n. That is the first order complete energy value after first order correction. Okay, I put that number 10. Now what we have to do is to find out the first order correction in the wave function. So that we'll do on the next class. And okay, I want to get your feedback of this kind of a method. First of all, I think it's taking more time than the slide presentation, but I thought since it is involving with equations, let me show it like this. But yeah, first of all, I think it's kind of if it is readable, and if you want me to follow, of course I think we will shift to slide way of presentation, because if you are going through like this, already you have a limitation of time. You cannot strain your eyes beyond a limit. So whatever we have to discuss, we have to, will be depending upon that, we'll be having less hours. Within half an hour we have to discuss the entire thing, and already the number of hours is also less. So we'll go with the slide presentation sort of, where we will be showing the equations and all, like that, whatever we had been doing. So I'll record that in that fashion and give you the recorded video. That will be much more easy, and in case if you want to follow the notes also, I think that will be much more convenient. Okay, so we'll stop here. It's already 40 minutes now. You give me your feedback about this kind of a thing. Okay, so yeah, that's it. Okay, tomorrow after you watch this video, if we we'll have some half an hour discussion if possible. Okay, then we'll stop here.